Alright guys, let's get started with today's lesson. So happy Merry Christmas and Happy New Year for the past holidays. Anyways, let's get started. Prime number. Prime number is a positive integer greater than 1 and only divisible by 1 in itself. Another way of saying this is that a prime number is a positive integer with exactly two factors, 1 and itself. The smallest prime number 2 which is an even number and the only even prime number. Theorem 1. There is an infinitely many prime numbers. There are infinitely many prime numbers. And 2, there is no greatest prime number. So how do we prove theorem 1? Well, there was a cool argument. I think it was Euclid who made this, and to show that there's infinitely many prime numbers. Alright? Assume that there are finitely prime numbers. We're gonna use it by contradiction. So let's assume that. Well, what happens after that? Well, notice that. Say the prime numbers were P1, P2. P1 is just 2, P2 is just 3, and so on. All this multiplied together to P sub n. Say P sub n is the greatest prime number we know of. And that's the max. Well, if we just add 1 to this number will not be divisible by 2, not be divisible by 3, and so on, and it will not be divisible by the nth prime. But this means that it's not divisible by any integer there. So it itself is a prime number. So this means that there are infinitely many prime, not finite. In theorem 2, there is no greatest prime number. Well, this is quite obvious. Why? Because if we already proved that there's infinitely many prime numbers. This means that there's no greatest prime number. Why? Because, well, if we have infinitely, there's always going to be one that's greater than the other. So it always keeps going. So theorem 1 is basically proves theorem 2. Now, a composite number is a number with 2 or more factors. And relatively prime is an example where two positive integers have no common factor except 1. The two positive integers are said to be relatively prime. For example, 4 and 9 are relatively prime. 1.2 dot. Method to determine a prime number. Theorem 3, the square root rule. It's a rule that you can use for this ability. If A is not divisible by all the prime numbers less than or equal to square root of A, then A itself is a prime number. Alright, this is a very key rule that can help you determine, how do I know if this is, well, how do we know that this number is indeed prime or composite? Let's move on. Example 1. How many prime numbers are there between square root of 51 and square root of 600? One way, which is probably the one that pops out to your mind the most, is just calculating the square roots. Well, what is square root 600 round to? When we round it to the nearest integer that's not greater than square root of 600. Alright, this just comes out to be 24, I'm pretty sure. 576 is indeed 24 squared. So I think pretty sure this works, right? Now, what is 51? Square root of 51. This is just 7 plus some random amount. Well, this is just 8, right? So this becomes 8 to 24. Now we just want to find how many positive integers are between, how many prime numbers are between these. Well, this is pretty simple. We just count. Well, notice that we can list them out: 11, 13, 17, 19, and 23. These are all the prime integers or numbers. So this means that example 1, there's an answer of 8. Since 11, 13, 17, 19, and 23 are all prime numbers, therefore there's 5. Right? Now let's move on to example 2. What is the smallest prime number greater than 120? A, 121, B, 123, C, 125, D, 127, E, 131. Well, how do we approach this? Well, notice that we can just use divisibility rules. Well, 121, we can easily see that this is divisible by 11. Actually, 11 squared, in fact. So we can rule this one out. 123, well, notice that the sum of these digits add up to 6, which is divisible by 3. So the answer is, so this one does not work. So the answer is it's divisible by 3. So it does not work. So it's just divisible by 3. For C, 125, this ends in 5, so it's never gonna be a prime number, except if it's just 5 itself. This just becomes divisible by 5. 127, well, what is this divisible by? What can we get out of this? Well, D and E look like the best options to choose as, oh, this might be the prime numbers. Well, how do we find out which one's which? Well, notice that 7 times 17 plus 1 is just 127. So 127 equals 11 times 11 plus 6. The what is 131. Well, it turns out that 131 is divisible by an integer. It's, well, this might be divisible by an integer. We don't know, but we want to check out this one first. It's the most important. So this also might be prime. We don't care. This also might be prime, but we want the smallest prime number, integer. This is just, notice that 7 times 17 plus 1 is equal to 127. So is 11 times 11 plus 6. Notice that since these do not work, and notice that the square root of 127 is 11. It's greater than 11, so it has to be all. We have to test out all prime numbers less than 11, and they turn out all don't work. So from here, we notice that 127 is the prime number, so that's the smallest prime number. So this actually might be divisible by something or divisible by not be divisible. We don't care, since we want the smallest prime number. That's the key thing, right? So the answer is D. Let's move on to the 25 primes up to 100. There are 25 prime numbers from 1 to 100. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, and 97. Alright? Now let's move on. Two prime numbers that are divisible by 2 are called twin primes. Find the sum of a pair of twin primes between 60 and 75. Alright, how do we put this? Notice that we have this beautiful grid given to us by whoever made this. Or you can just derive it by yourself, or we can say it's you. You made this. Anyways, well, how do you push this? Well, we want a sum of pair twin prime between 60 and 75. Well, what are they? 61 doesn't work because obviously 61 obviously does not work, right? It's nothing near it, except for 59, which is less than 60. 67, similarly. Now, 71 and 73 do work. Why? Because they're two-way. You can fill it in with a 72 right there. These are two-way. Plus 1, plus 1. Now, this just means that they are 2 apart. This means this is the twin prime. So we just have to add them up. 71 plus 73, which just gives you 144, or D. Alright? Now let's move on to problem skills. Property 1. A prime number P can only be written as P times 1. In other words, a prime number P can only be divided by without a remainder by itself and not 1. If P is a prime number, and P is equal to n times n, then one of the two numbers and n must be 1 and the other must be P. Find the value of the positive integer x such that when 64 is taken away from it, the result is a square number. And when 25 is added to it, the result is also a square number. I'll ask you guys for trying this question and tell me your answer through chat. Alright, let's get started with this question. So basically, how do we approach this? When notice that 64 is taken away from it, the result is a square number. 25 is added to it, it's also a square number. What does this mean to us? Well, let's try it on every single integer. Let's start with 1,400. 1464, I'm pretty sure it's not a square number. Right? What about 16? 1664, is it? Well, I have its doubts. What about 125 plus 64? Let's think about this one. If we add it, it becomes 1191. Is that technically a square number? The ones I want to compare is 1191, 2044, 1664, and 1464. We want to see if these are square numbers. 2044 is not clearly not a square number since last year, 2025, was a square number. And 2025 is 45 squared. 46 squared is going to be way past 1044. So we can rule this one. What about 1664? Well, what can you see about this one? This was divisible by 16. That's a square number. Once we factor it out, we get 104. This clearly is not a square number. So we can rule this one out also. Now what's left is 1464 and 1191. My suspicion tells me it should be 1191, but let's see. Right? So, how are we supposed to do this now? Well, we can just factor. 1191 is just divisible by 3, right? Since 3 plus 9 is 12. Well, that doesn't really work. Why is that? This one is just 3 times 1191 should be 117, if I'm correct. It should be 39. Yep, that is the calculation. 3 times 39 and 17. Nice. Well, does this technically work? This really isn't divisible by any integer, actually. Pretty sure it really isn't divisible by any integer. So this clearly is not a square. Let's reread the question. Find the positive value integer x, such that when 64 is taken away from it, the result is a square number. And when 25 is added to it, the result is also a square number. What? Alright, my bad. We're supposed to take 64 away from it. Oops. I did it all wrong. So make sure you read the question carefully. Don't go off on a random path. It's okay if you do, but you gotta make sure that you read it carefully first. Alright, so 60, we find a number and we take away, and when 25 is added to it, is also a square number. As we talked about before, 2025, the year before, was a square number. So 2000 is going to be the answer because 2025 was a square number. And 64 away from 2000 is, I'm pretty sure, 1936, which is indeed also a square number. So 2000 is our answer, or D. Alright. Let's move on to example 6. Find the value of b minus c if a cubed equals b squared, c squared equals d, and d minus a equals 5, where a, b, c, d are positive integers. Let's go to try this question and tell me answers through chat. Let's get started with this question. So basically, how do we approach this? Well, first off, this is probably going to be hard. Why? Because a cubed is equal to b squared. That's really hard to get. But it's not necessarily hard, technically. Well, if we think about this, a cubed, how do we get a cubed to be equal to b squared? Well, if a and b were equal to 1, this would work, right? But you know that d minus a is equal to 5. So then d had to be 6, but 6 is not a square. So A must have been a perfect square, and B must have been the perfect cube, a perfect cube. So we can let B be equal to 8, up 2 cubed actually. 8 is 2 cubed, and A as 4 cubed. 8 is just 2 cubed, and we square that, 8 squared is equal to 4 cubed. Now, once we got this, notice that C squared equal to D. Well, how do we get this? Well, this is just C squared. So you want to square minus 4, that is equal to 5, which obviously comes down to 3 squared minus 4, which is equal to 5. So D is 9. So then B is 8 and C is 3. 8 minus 3 is 5, so the answer to this question is just A. Alright, let's move on to example 7. The sum of two prime numbers is 39. What's their product? Let's go try this question and tell me the answer to chat. Remember, there's a really quick way that requires one trick, right? So I'll give that hint, and I'll let you guys have a try on this question. All right, let's get started with this question. So there's a really an idea behind this. Well, notice that first off, how do we get a sum of two prime numbers that is equal to 39? Well, we can do it by even or odd, or it's actually only one way. There's even and odd, right? Or odd and odd gives even. Even gives also even. So it has to be even or odd even. So this is telling you that one of the prime numbers must be even. And we know that for sure that there's only one prime number that's even. That's two. Alright? Two. This implies that then that other integer is 37. Multiplying this all together is just 74. So the property 2 is important. A very important way to tackle these questions. These have been in the past AMC 8s, AMC 10s before. So you don't need to memorize it, but just memorize that using this fact can help you in so many ways. Alright? Let's move on to example 8. Sum of two prime numbers is 49. What is the sum of the reciprocals of the two prime numbers? I was going to try this question and tell us through chat. Let's get started with this question. So how do we approach this now? Same exact way. We talk about two, right? You must have a two when it's an odd. Add up is odd. So it'd be 2 and 47. Right, now we want the reciprocals. That's the most important part. The reciprocals of each prime number. And we're going to add them up. So it just becomes 1/2 plus 1 over 47. Using our normal fraction addition, find the least common denominator, add them all up, you get your answer as 49 divided by 94. Since 47 plus 2 is 49, and the least common denominator is 94. Times B. Alright? Now let's move on to example 9. Three prime numbers P, Q, and R satisfy the following conditions. P plus Q is equal to R, and 1 is less than P less than Q. Find the value for P. Let's get the try this question and tell me answer to chat. Let's get started with this question. So basically, notice that three prime numbers such as P plus Q is equal to R and one is less than P is less than Q. Then this tells you that Q is even or P is even. In this case, P must be even since P is less than Q. So we already know that P is 2, 2 plus Q is equal to R. So all we're trying to do is find a twin prime. Right? But this since we already found one value of P, it's just telling you the answer is just 2 or A. Alright? Let's move on to A plus B. Example 10. If A plus B plus C plus 66 is equal to 66, and AB plus BC plus CA is equal to 1071, where A, B, and C are all prime numbers, find the value of ABC. And let's get up and try this question in 10 minutes in chat. Let's get started with this question now. So how do we approach this? Well, notice that first of all, that A plus B plus C must be equal to 66. So it's just an even and an odd and odd. So A could be 2, and B and C have to be odd numbers. Or an odd numbers that are summed up to 64. Well, with guess and checking, we're gonna arrive at this conclusion that A is 2, B B is pretty sure B times C is 943, if I calculated correctly. Let me check again. So BC is 943. So this just means that there has to be two primes that multiply out to 943. And we just go searching for it. Or you could just use it from guess and checking. Well, this arises for us, it arrives at 2, 23, and 41. So from here, the answer is just this multiplied together, or 1886. Alright, now let's move to example 11. For how many positive integers is n squared minus 3n plus 2 is a prime number? Well, notice that for this case, quite obvious that we can just use, all we can actually use is just factorization. You can factorize this by yourself using FOIL or whatever you want to do, whatever method. But it's just a binomial factorization, trinomial factorization. Search it up on the web how to learn about this. But to keep it simple and quick, we can factor this to n minus 2 times n minus 1. So n minus 1 has to be equal to 1 or n minus 2 equals 1. If n minus 1 equals to 1, then n minus 2 is 0. So we must have n minus 2 equal to 1. This means n must be 3 and n minus 2 is 1. So it'd be 1 times 2. So it'd be 2. And that's a prime number. Right? Of this, there's no possible way. Why? Well, that's because once we go up, these will be prime numbers or composite numbers. But that will mean that the multiplication after you multiply is just going to be composite. So the answer to this question is just 1 or B. Let's move on to example 12. The positive integers a, b, a minus b, and a plus b are all prime numbers. The sum of these four primes is even, divisible by 3, divisible by 5, and divisible by 7. A, B. One of them must be even. These are both have to be odd. So this is odd, this is odd, this is even, this is even. If we add this all together, we get 3a plus b. I mean, this is three evens. I mean, three odds and one even. This will be also, this will, this will be odd, odd, odd. If we add this all up, this will also be odd. So what else can we get from this? Well, these will definitely not, or might be prime. Well, these are all odd numbers, right? 3a plus b is not divisible by a or b. Like, these are all prime numbers. 2 times a, 3 times a is divisible by a. It's divisible by a or 3. But b is a prime number. If we add to that, then 3a plus b will all both not be. These will make it so that it's not prime. So the answer is just E. Alright, so this from here is just making it divisible by 3 and a. But if we add a b, this is also prime. This makes it prime also, because there are no possible factors. Right? Now let's move on to example 13. The product of three prime numbers is 5 times the sum of these prime numbers, and it's also divisible by 5. 5 the remainder when the sum of these prime numbers are divided by 11. I was going to try this question and time answer to chat. Let's get started with this question. Well, how do we approach this now? Well, notice that, first off, since the product has to be divisible by 5, we must have 5 times P times Q. Notice that this is equal to 5 times P plus Q plus 5. Alright, of this. Well, we can do some casework after we get to PQ minus P minus Q plus 1 after expanding and simplifying. Or P minus 1, if you know Simon's favorite factoring trick, is equal to 6. You can do some casework from here, but you'll eventually notice that P can be equal to 2 and Q equals 7. Or vice versa. Therefore, the three prime numbers are 2, 5, 7. And the sum is 14, and the answer to that is 3, since the remainder is going to be 3. 14 minus 11 is just 3. Alright, that's it for today's class. I hope you guys have a wonderful weekend. I'll see you next week. Bye.